In this video, we're going to graph quadratic equations. Those are equations with where y is equal to x squared plus something else. We're going to graph some kind of relatively basic ones. We're going to compare them to the most basic, or the parent function. And then we're going to use our graphs, in particular our computer aided graphs, to find something called zeros, which are very important things, and one of the primary reasons why we bother graphing parabolas in the first place, or any function in the first place. First note that we say that the zero of a function is any input that makes the output zero. So any x's that make y's zero. On a graph, that's where a graph would cross the x-axis. Those are the x-intercepts. So if we say find, or if you're asked to find the zero of a function, you want to know what x's do I plug in so that I get zero back out. A really common mistake is to plug zero in and see what you get. That is not what a zero is. That would find the y-intercept, but that is not necessarily a zero of a function. For each of these, we're going to do some quick graphing. We're going to use a calculator, whether that's your Inspire, or I'm going to use Desmos today, to graph and compare some graphs, and then we're going to use those graphs to state some zeros, and we'll round to hundreds if we need to. If you needed to graph these by hand, we would graph these in exactly the same way we've graphed every other function family up to this point, where we have a basic function. We're going to figure out some properties of this base function, or this parent function, and then we know how to transform it by looking at the equation, like sliding it up or down, sliding it left or right, stretching it, and so on and so forth. And we've done that in the past with absolute value functions and exponentials and lots of things. This exact same thing applies here. So we're not going to spend too much time talking about those, talking to the actual like details of the graphing. We're going to let our calculator, or in this case Desmos, do that for us. But we're going to interpret these graphs by looking at the equations and looking at the pictures. So our parent function is this base parabola y equals x squared, and that looks like this. On Desmos, you do not need to type the y equals part. And when I type y equals x squared, or the function x squared, I get a shape that looks like this. This is called a parabola. It's like this basic U-shaped thing that is getting ever taller and ever wider as you go. So it never goes straight vertically up. It always is going out to the right or left. It has a special point called a vertex, which is down here at the bottom. And this is where the highest or the lowest point of this parabola is, or the maximum, or in this case, a minimum. And what's nice is on Desmos, you can click on this vertex or any of these zeros, and it'll automatically show up. So this has a parent function as a vertex down here of 0, 0. We're going to quickly graph these new parabolas, and we're going to compare them to the original. So if I want to graph x squared now plus 1, this graph in blue is that graph, y equals x squared plus 1. Maybe I'll zoom in a little bit. Unsurprisingly, it's a little bit, it's almost the same thing as the original graph, just we've added 1 on the outside of this function. So I think, as we saw in the past, adding 1 on the outside of the rule of this parent function is going to slide this graph, and it's going to slide it up by 1. So every point that was on the red graph is now on the blue one, just it's 1 higher. So when I'm asked to, if I need to sketch a graph of this, I can do that. I'll quickly, oh boy, that's really bad. I'm going to try to draw some axes in real fast. The best of my ability, and you can see my ability is pretty bad here with my computer, but I'm going to try. And I think looks like I start here at 0, 1, and I'm going to go ever wideningly out, oh boy, that is a really bad parabola. That's why computers are so much better at doing them by hand. Note the computer parabola is not wave in and out. Maybe we stick with the computer graph. But I can graph, one thing I noticed about this again is that what I can do is write down some comparisons between these two. And it definitely looks to me like my new function here is the old function, but slide up by 1, or vertically translate it up by 1. State the zeros. Where does the blue graph cross the x-axis? It does not. So there are no zeros, because this graph does not ever cross the x-axis. In contrast, how about we graph this second one, y equals x squared minus 2. I'll clear out this blue graph and let's add a new one. I'm going to leave the parent function so we can compare easier in the end. Put x squared minus 2. Now this green graph is, unsurprisingly, it's the original one that slid down by 2. Slide down. I can make that comparison. And when I look at my graph, this time there are zeros. There are zeros to this graph because this graph crosses the x-axis twice. So on Desmos, I can just click on these points. And these inputs that make the output 0 are negative 1.414 and positive 1.414. Or to the nearest hundredths place, about negative 1.41. And x equals positive 1.41. More specifically, you can show, you could find these zeros algebraically by setting y equal to 0 and solving for x. And if we saw in our solving quadratics unit that you could get x squared by itself and use a square root, and these numbers are not coincidentally the square root of 2 and minus the square root of 2. A little more complex one. Maybe I take a second before you maybe pause the video if you'd want and try to guess what you think this graph should look like. Okay, hopefully you've taken a guess. I think this graph is going to be slid up by 2 because I've added 2 on the outside of this thing, and it's also multiplied by negative 3. Let's see if I remember right from our previous lessons. Multiplying by a negative to the function flips it upside down, and multiplying by numbers on the outside of my function stretches this thing out. So I think this is going to be upside down, stretched a bit, and then also slid up by 2. And let's check to see if that works. 3x squared plus 2. What do you know? It looks like this graph is upside down. It's definitely more stretchy in the vertical direction. I mean, it's pulled further vertically, so it's narrower in a sense because it's increasing 3 times as quickly. And the vertex has gone from 0, it's slid up 2 spots. So what do you know? It looks like my prediction was right. So what comparisons? This was a vertical stretch. By a factor of 3. This is reflected. And this was translated or slid up by 2. What are the zeros? The zeros were across the x-axis here. Let's find them. I'm going to click on the green zeros here, and it looks to me like the zeros in this case are x equals negative 0.82 round to the hundredths place, and x equals positive 0.82 to the hundredths place. Another example, here's a new function, x equals this crazy thing. For each of these 2 transformations, we're going to describe what's happening to this function, and then we're going to write an equation to represent what g is. So the base function is negative 0.5x squared plus 2, and we're going to build a new function by taking that one and subtracting 7. To me, it doesn't matter what the parent function is. This subtract 7 on the outside of the function tells me that I'm taking whatever that old function is and I'm sliding it down. And I'm going to slide it down by 7. So I think this is a slide down by 7. So g is going to be whatever this original thing is, but slid down 7. How do I come up with what this is going to be? Well, you can really think of this as substitution. we've substituted things before. F is this rule. So maybe I take F out and I put this in its place, and then I just take away 7 from it to get a new rule for G. So I think G is the rule for F, which is minus 0.5 x squared plus 2. And then I take away another 7. And I can get a rule for G by combining the like terms. Looks like 2 and negative 7 will combine together to be minus 5. And note that minus 5 is 7 units below positive 2. Kind of similar game. I think that the graph of h is going to be whatever x is, but added 1. So I think this is, because of this adding 1 on the outside, this is a slide up by 1. And just as before, I think we can come up with what this equation is by taking f and substituting in it, and then just adding 1 to the rule. Negative 0.5 x squared plus 2, then I add 1 more. So I think h of x is negative 0.5 x squared plus 3, because 3 is 1 more than 2.